Hi all. Because in Unit 8 we are learning about enolate chemistry, it is essential that we have different methods to make the enolate. And here we have two examples, one using LDA and one using NaOH. And both methods are important for us to learn. If you take a look at our starting ketone, you'll notice that we have two alpha carbons. And depending on which carbon you deprotonate, we could get two different enolate anions. One with a double bond on the right, the other with a double bond on the left. I've labeled these two types of enolates, the kinetic enolate and the thermodynamic. And based on which base we use and the conditions, we can choose which one we want to be the major enolate. So what is the difference between the kinetic and the thermodynamic enolate? Very simply, one can think of the kinetic as the one that is made faster, whereas the thermodynamic is the one that is more stable, the more stable product. So one might wonder, how can we have a reaction where the product that's made faster is not actually the one that's more stable? One way we could visualize that is via a reaction energy diagram. Let me sketch one out for you right now. We get a situation where the kinetic product is different than the thermodynamic product when it is much easier to get the kinetic because the activation energy is lower. So here I have it illustrated in green. The activation is the hill. To get over is easier to get over the green hill than the red hill. So that tells me that the green line indicates the kinetic product, the product that's made more faster or made faster. The thermodynamic product, though, it's determined because the end result is more stable, but in this case the hill is much higher to jump over. So this is, again, one situation where the thermodynamic product and the kinetic product are different. And this one is more stable. There are many reactions where the product is both the kinetic and thermodynamic, but in case of enolates, where you could have two different enolates, typically there is a difference between the kinetic and thermodynamic product. Now, I do have both of these lines a little bit higher than the starting ketone. That's because we make the anion, which is a little less stable than the neutral starting material. So here I've drawn the compounds that are represented at each of these energy levels. Now, I haven't mentioned yet, and you may wonder, well, why? Why is the green enolate the one that's made faster, whereas the red one is the one that's more stable? For the green enolate, we are deprotonating the alpha carbon that is more accessible. So we could say that this alpha carbon is less crowded. And when you run the reaction at low temperatures, under kinetic conditions, you will make the kinetic product, which is made faster. I'll talk about these reagents in just a bit when we look at the reactions specifically. But what about the thermodynamic product? Why would I consider this the more stable? Quite simply, it's because it's the more substituted double bond. I would say that this is tetrasubstituted, whereas this is trisubstituted. Now that we have a good idea the difference between the kinetic and thermodynamic, between this one that's made faster versus this one that is more stable, and we also see visually what kind of reaction coordinate diagram we have in terms of energy and the activation energies needed to get to both of these products, let us look specifically at the reagents. If we want to enrich in the kinetic versus enriching in the thermodynamic product. The first reaction is reaction A. We have LDA at very, very low temperatures and this tetrahydrofuran. Let me draw a couple of molecules so you know what these look like. It's a little bit tight, but THF tetrahydrofuran is the solvent, and it looks like this. We'll call this a polar aprotic solvent. And LDA is lithium diisopropyl amine, which is a very strong base. Let me draw you out the mechanism. There is something that I want you to notice, that we have a full arrow here, and we are going to make, since this is such a strong base, we are going to make nearly 100% of the enolate, and 100% of that is going to be the kinetic enolate. Okay, for reaction A, I have the starting material and the products drawn out here. The mechanism arrows, again, you want to start from a source of electrons. We are deprotonating the carbon that is more accessible, less crowded in other words. You are going to form the oxygen anion enolate, which I have right here. We now know this as the kinetic enolate. Again, we are stripping off the hydrogen off of the alpha carbon that is less crowded. And I also drew us the conjugate acid. Why do I want to do that? Because this is actually an acid-base reaction to form the enolate. This ketone, you've memorized the pKa's hopefully by now. The ketone is, the aldehyde has a pK of 17. Ketone is a little bit higher. It's around 20. Do you remember the pKa for the amine? pKa for amine is around 36. There's a 16 pKa unit difference. So essentially we get 100% of the products. I have a full arrow here. Okay, I have a full arrow here. And we are favoring, right? We're favoring the weaker acid. Later on, when we look at some of the reactions for this unit, it's going to be important that we understand that if you use LDA, that you're going to form the enolate in 100% yield. Essentially 100% yield. I also have drawn here the resonance. You know, you could get the resonance structure of the enolate by moving these electrons like such. Okay, this is still the kinetic, right, because it's coming from the kinetic enolate up here. So there are two ways to show or to represent the enolate, either via the oxygen anion or the carbon anion. Okay. For my class, when we draw mechanisms of reactions, we are going to draw the oxygen anion enolate because it is the more stable or the more major contributor, resonance contributor between these two. Alright, so that is the story for LDA. Again, because the pKa is much higher on the right, we are favoring the right side, and we are favoring definitely the kinetic enolate. Reaction B to form the enolate also has some interesting features. Here I have drawn the two starting materials, again, the ketone, and here now we're using sodium hydroxide. You know that this is ionic, so in solution you want to separate those two, the Na plus and the OH minus. Why don't you pause the video and draw me the mechanism and the products, and if you can you predict the equilibrium arrow? You may wonder, if just given the two starting materials, or the base, how can we tell if we're going to make the kinetic versus the thermodynamic enolate? I didn't quite mention that. For LDA, we're going to list this as a very strong, bulky base. Strong, bulky base. So there has two things going for it. It's very strong, so it's going to strip off a proton quickly, very fast. Plus it is crowded, so it is less likely to strip off the proton on this alpha carbon, which has this methyl group. Strong bulky base, go for the less crowded proton. Yes, in the past we described hydroxide as a strong base, but actually it's not as strong as LDA, so we could call this a moderate base, and it's not bulky. moderate base. Therefore, we are going to strip off this hydrogen, and it's mainly not just because of the base, but because we are going to form the more stable enolate. So that's part of the motivation. Now we're forming the more stable enolate, and it's more stable because the carbon-carbon double bond is more substituted. We did create water. That's going to be important for us when we draw the equilibrium arrow. Alright, so again, the main difference between LDA and OH minus, not only that they give us the two different enolates, but LDA is bulky and a little bit stronger than the less crowded OH minus. Now take a look at our acid-base analysis. We want to compare the two acids. Again, the pKa for the ketone is 20. But what about water? The pK for water is less than 20. It's 15.5. Do you see? That's a huge difference. Here we have 20 going to 36. Okay, favoring the right. But here we have 20, and on the right side we have 15.5. Now we're going to favor the left. So with NaOH, there are two things. We make the thermodynamic enolate, for sure. But also, we are actually favoring the ketone. So we get a small percentage of this overall. So in this type of reaction, it's interesting, we get some enolate, but mostly the ketone, aldehyde, or ester. We could call this carbonyl, right? The one that's not an anion. You may ask, well, that's not good. Aren't we supposed to strive for high yield? In the first reaction we're going to see, it's actually beneficial for us to have a little bit of enolate and mostly carbonyl, because we're going to make these two react with each other. So we need some of this unreacted. Later on in the unit, we're going to aim for the kinetic enolate because we want 100% of the enolate. We don't want any of the unreacted carbonyl. Bottom line is, both reactions are super important, and we'll see that depending on the type of reaction we want to do, we could either choose to use LDA at low temperatures or NaOH.